Merry Christmas, everybody. I'm Vasileios Moutsios from the University of Pittas, PhD candidate, and I will present you our study on the evaluation of air equations of state. I have to know that I presented a different presentation for PowerPoint, so in PDF we will have some changes, but we will figure out a good way to present it. Okay. So, okay. Okay, let me tell you all the story. We were designing an air compressor, so we used the software Safe Turbo. For the Safe Turbo, provide 6 models to uh, predict the properties of air. So we had the question which model performs better in our case. We searched for publications, but we didn't find a clear comparison of these models and with the area of interest. So we realized this analysis. The 6 models are shown here that are available in the Safe Turbo, and so we started to perform the analysis. The steps for the analysis was to find the real values of air in order to compare with the results of the models. Then we use the models to calculate the properties of air. Then we calculate the deviation of each model from the real properties. We verified the results, and then we came to the final conclusions. So, we found these values for the real properties of air in 4 sources. And also we found a 5th source that had a 1% deviation of these values. The range that we will perform the analysis is 1 bar to 250 bar pressure and 250 Kelvin to 800 Kelvin temperature. So we used these equations to calculate the properties of air in the desired range. Only for the 6th model, the cool probe, we didn't create the equation because it is a S++ library with several equations. So we just use the online calculator of the cool probe who created the software. Then we calculated deviation of each model. I have to note, you see in this slide, that each equation is solved to the pressure. So we choose to calculate the pressure in each case, so to avoid any calculation and roundup errors. So we calculate the deviation of each model. In order to make the evaluation easier, we colored the deviations. The best one, the more precise, with 0.1% deviation is with blue. Then we have between 0.1% to 1% deviation with green, 1% to 10% with orange, and well, the worst case, 10% deviation and above with red. So here we will have an animated thing, but it's not, so I will show you the other available slides. So these are the 2 first equations, the perfect gas and the Redlich one. We see that perfect gas has a region with very low precision, while the Redlich one performs relatively good with maximum of 3.5% deviation. The other 2 are the Onion Redlich one, which is better than the Suave Redlich one, which is also in the same level of accuracy in different areas. We see that the Onion Redlich one has better performance in low temperature, high pressure, while the Suave Redlich one has better performance in high temperature, high pressure. And then we have the Penck-Robinson, which was not so good, and the cool probe, which was the best. As you can see, it has a maximum deviation of 1%. So, let me go back. In order to verify our results, we used online calculators. We just calculated the difference of our models with the online calculators. Where you see the minus, it is where our models performed better. So you see that in all we performed better instead of the Redl squad, which was slightly better than ours. So we consider that we did a very good job. So the conclusions, we would also have here an animation, so we will go back to the... Okay, as we can see, the cool prop is the best option, but as I told you, it's very difficult to create it. So the other best options, if you want to create something on your own, is the Anier Redl squad and the Suave Redl squad, which depends on in which area you want to work. If you want to design or study a phenomenon in low temperature, high pressure area, you will use Anier Redl squad. Or if you want to work in the high temperature, high pressure, you will choose the Suave Redl squad. So you can see here, these two models have a common area of low precision, but you can say it's not so bad as in the worst case scenario, you have a 2% deviation. So maybe, it depends on the application, this deviation may be acceptable. So that were the conclusions. Let me see if I forgot something. No? Okay, thank you for your attention. It depends on the application. Some very precise applications like aerospace applications, they will need very precise results. Like industrial, maybe at 5% will be adequate because they don't care so much about safety factors, let's say. They have more margins for mistakes. So they don't care so much about precision. Thank you.
What about numerical errors in the... you use finite elements, I think?
No, we created these formulas and we calculate the values with these formulas. I have to know that the real values that we compared the calculated values were by bibliography, which may be results from experiments, from other calculating methods. So there are errors everywhere.
Okay, thank you very much.